Hello, my name is Long, and this is for quiz 1. For problem 1, it tells us to find equilibrium points and determine whether each is stable or not for the differential equation. In this case, we have dx over dt, or the derivative of the function f of x with respect to time, equals to x in parentheses times x squared minus 4 times in parentheses x minus 3 squared. First, we have to find the equilibrium points, and to do that, let us set the function equals to 0. And after that, we have to solve for x, whatever equals to 0. I notice that in the original function, we have x squared minus 4, which could be factored out to x minus 2 and x plus 2. So after some calculations, we solve for that the function is equal to 0 when x is equal to negative 2, 0, 2, and 3. After that, we have to graph each equilibrium points, and we have to plug in points between each equilibrium to see whether it has a negative or positive slope, which tells us where each point converges to. If both points above and below the equilibrium converges to the same equilibrium, then it is stable. If both points converge away from the equilibrium, then it is unstable. But if one point converges to the equilibrium, another point converges away, then it is semi-stable. In this problem, we have that at the equilibrium 3, if we plug in the point 4, we're going to have a positive slope, but if we plug in the point 2.5, we're going to have a positive slope, which heads towards the equilibrium, while 4 heads away from the equilibrium. So this is semi-stable. While between the points 2, we have, if we plug in the point 1, we're going to have a negative slope, which converges to 0, while we have 2.5, which we said converges to 3, it makes the equilibrium 2 unstable. And so, if we have equilibrium 0, you have the point 1 converges to 0, and the point negative 1 converges up to 0, so this makes it a stable equilibrium. While with the 2 points between the equilibrium negative 2, we have 1 converges away, negative 1 converges away, and negative 3 converges away, which makes this unstable. This is for quiz 1, question 2. We have here that the problem says describe all the possible behaviors as t or time goes to infinity. A solution starting at x is 0 equals to 1 for the equation below as k varies over real numbers. We have here that they give us a function of d of x over dt, or derivative of the function f of x with respect to time, equals to x times, in parentheses, k minus x squared. So, similar to problem 1, we have to find the equilibrium points. And so, all we need to do is set the function equal to 0 and solve what x equal to get 0. And so, we have here that this function is equal to 0 when x equals 0, square root of k, and negative square root of k. To solve for square root of k and negative square root of k to make the function equal to 0, all we need to do is factor out k minus x squared to get x minus square root of k in parentheses times x plus square root of k in parentheses. And so, after we figure out all the x's to make the function equal to 0 for our equilibrium points, we see that if we plug in k greater than 0, the equilibrium point should be around square root of k, 0, and negative square root of k. But if it's k less than or equal to 0, the equilibrium point should be 0. But because it says that any behaviors of t is greater than t going to positive infinity as time can be negative, we don't have to worry about the negative square root of k. And so, if we graph it out of each behavior, we see that if we plug in a k greater than 1, we see that at the initial point of x is 0 equals 1, it's going to converge up positively to a positive square root of k. While we have when k equals to 1, it would just converge neither up or down and just have a flat slope of 1, like so. But if you have a k between 0 and 1, we're going to have at the x of 0 equals to 1 initial point, have a negative slope down, which is below the 1 and above 0 to have square root of k at the equilibrium right here. Well, if we have a k less than or equal to 0, we're going to have the initial point converge down to 0, but when k is equal to 0, we're going to have it converge straight out to 0 and have a flat slope.